pokoknya mengalir saja, Pak.
Oke, sukses selalu, Prof.
Oke, Pak Nyoman, matur nuwun, Bapak Ugi, sehat-sehat Pak Nyoman.
Oke, sehat. Ya, saya di kantor nih, Prof.
Wah, tapi belum masuk kan ya, kuliah?
Belum.
Ya,
masih virtual.
Masih virtual ya.
Masih virtual ya. Terima kasih sudah berkenan hadir.
Ya, Pak Nyoman, matur nuwun sudah di-invite. My pleasure lah pokoknya kalau untuk BMKG, STMKG.
Ya, terima kasih, Prof.
Ladies and gentlemen, may I have your attention, please? For the participant, please mute your Zoom. And then our webinar is about to begin. Please have a nice seat and be prepared. The Honorable, our speakers, Professor Dr. Matthieu Kervyn from Fiji Universiteit Brussels, Professor Dr. Renat Muhammad Aris Marfai, S.Si, M.Sc, as the head of Indonesian Geospatial Information Agency, Professor Teguh Faisal Fathani, STMKG Ph.D. IPM from Gadjah Mada University, Honorable Dr. Nelly Florida Riyama, S.Si, M.Sc, as the head of Center for Research Development of the Indonesian Agency for Meteorology, Climatology, and Geophysics, Honorable the Chiefs of the Center Meteorology, Climatology, and Geophysics Agency in Region 2 and all of the BMKG employees, Honorable Dr. Nyoman Sukanta, S.Si, M.Sc, as the Chairman of School Meteorology, Climatology, and Geophysics, Honorable structural and non-structural officials, lecturers, and staff, and all of the cadets of School Meteorology, Climatology, and Geophysics. Distinguished ladies and gentlemen, good afternoon. Welcome to the International Webinar of School Meteorology, Climatology, and Geophysics. First of all, we would like to say Happy World 71st Meteorological Day and thank all participants for the willingness to take part on this webinar. It's been a great honor for me, Janita, to be the master of ceremony and welcome each and every one of you in this Zoom meeting. Before we come to the main session, let's start by praying first, so the event will run well without any obstacle at all. Pray based on individual belief begins. Praying enough? On this day, we have several agenda as follows. The first is opening ceremony. The second is opening speech. Third is main session, that is discussion from the speakers. And the last is closing ceremony. Ladies and gentlemen, we would like to invite, and we will start this webinar by singing the national anthem Indonesia Raya and March BMKG. Ladies and gentlemen, we would like to invite Dr. Nyoman Sukanta, S.Si, M.T, as the Chairman of School Meteorology, Climatology, and Geophysics to deliver his opening speech. Dr. Nyoman, time is yours.
Thank you, MC. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good afternoon, Honorable the Speaker, Professor Dr. Matthieu Kervyn, full-time senior lecturer in Physical Geography at System Science and Department of Geography, Vrije University, Brussels. Professor Dr. Renat Muhammad Aris Marfai, S.Si, M.Sc, head of the Indonesian Geospatial Information Agency. Professor Tengku Faisal Fathani, STMKG, Ph.D, IPM, head of Department of Civil and Environmental Engineering, Faculty of Engineering, UGM. Head of Center for Research and Development, BMKG, head of the Center of Meteorology, Geophysics, Agency Region 2, Ciputat, head of Tangerang Geophysical Station, head of Meteorological Station in Jakarta and its surrounding, structural and non-structural official at STMKG, lecturer and staff of STMKG, and all participants for the 71st World Meteorological Day Seminar. Praise be to the presence of Almighty God for the grace that has been bestowed on all of us so that we can virtually gather to carry out the 71st International Web Seminar for World Meteorological Day 2021. Ladies and gentlemen, the commemoration of World Meteorological Day is an annual agenda held by STMKG. This webinar activity is the first international webinar we hold on a routine commemoration of World Meteorological Day currently in 2021 due to the COVID-19 pandemic. STMKG is again commemorating the 71st World Meteorological Day by holding an international web seminar with the topic of the ocean, our climate and weather, where has been released by World Meteorological Organization. Ladies and gentlemen, we need to say STMKG has been involved in various activities and research related to ocean, climate, and weather for years. Since 2015, STMKG has annually participated in the research mission of the Indonesian Program Initiative on Maritime Observation and Analysis, or INAPRIMA, in the Indian Ocean in collaboration with national and international institutions. From 2017 to 2019, STMKG carried out research and development activities for the landslide early warning system in Banjarnegara, Central Java. In addition, in 2019, STMKG conducted flood research activities on the north coast of Central Java. And most recently in 2020, STMKG is involved in organizing the International Conference on Tropical Meteorology and Atmospheric Science, which is also an initial series of these World Meteorological Day activities. Ladies and gentlemen, the 71st World Meteorological Day International Seminar has a goal to add insight to seminar participants in exploring the science of atmosphere, and environmental science related to marine, climate, weather, and natural disaster in Indonesia. The 71st World Meteorological Day Seminar is also aimed to increase the enthusiasm and motivation of seminar participants to continue observing, studying, and researching ocean system, environment, and atmospheric phenomenon. We hope the output of this seminar activity also will increase the awareness of the audience and community to pay more attention to the condition of marine waters, climate, weather, and natural disaster due to the impact of climate change and extreme weather in Indonesia. Ladies and gentlemen, by saying Bismillahirrahmanirrahim, we are proud to declare the International Web Seminar on 71st World Meteorological Day officially open. I hope this web seminar will run smoothly and all participants can enjoy the moment and to exchange experience and work together on this day and the future. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. Shalom. Om Santi 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 Om.
Thank you, Dr. Nyoman, for the opening speech. Ladies and gentlemen, as you know, this webinar is held to celebrate the 71st World Meteorological Day in the theme of the ocean, our climate, and weather. This webinar also provides you plenty of opportunities to discuss, share knowledge and insights. Besides of that, it also a platform for the participants to add your knowledge on meteorology and atmospheric science, climate and weather. Ladies and gentlemen, it was such an honor to the committee to have a prominent of expert speakers on this webinar. Now, before we move to the next agenda, we would like to invite all participants to turn on your camera as we will have to start the photo session. So please, for all the participants, you may turn on your camera. We will start from the first page. Get ready, everyone. Please turn on your camera. Okay, thank you. Next, we will move to the second page. Once again, I remind you to turn on your camera. Okay, thank you. Next page, please. Get ready, everyone. Thank you. We'll move to the next page. I remind you to turn on your camera. Okay, thank you. And the last page. Get ready, everyone. You may smile too. Thank you so much. Ladies and gentlemen, before inviting the moderator, we will deliver to you a short, brief biography of our moderator today, Mr. Amir Mustofa Irawan, M.Sc. Mr. Amir Mustofa Irawan is the head of STMKG for Research and Community Services Unit and one of the lecturers in the Department of Climatology, STMKG. And for his education, he completed his Master of Science at Department Geography and Planning University of Liverpool in UK. And his expertise are environment and climate change. And now we will begin the interactive discussion. Ladies and gentlemen, we have the honor to invite Mr. Amir Mustofa Irawan.
Well, thank you very much for the Master of Ceremony, for the MC to provide my CV. Good evening, everyone, and good morning from the Brussels time. Ladies and gentlemen, Excellency, the Chairman of the STMKG, Excellency, the Head of the Center for Research and Development, VMKG, Excellency, Head of the Meteorological Stations, Climatological Stations, and Geophysical Stations around Jakarta, and also Excellency for all of the lecturers in STMKG, our scientists and researchers from the Indonesia Agency for Meteorology, Climatology, and Geophysics, BMKG. Thank you very much for joining us in the International Seminar on the 71st World Meteorological Day. All right, so as is stated in the agenda, we have 3 keynote speakers. So please welcome to our very special and prominent speakers. The first is Professor Dr. Matthieu Kervyn, who is the full-time senior lecturer in physical geography, Earth System Science, and Department of Geography, Vrije University, Brussels. And our second speaker is the Professor Dr. Renat Moh Aris Marfai, S.Si, M.Sc, who is the head of the Indonesian Geospatial Agency. And the last speaker is Professor Tuku Faisal Fathani, STMT Ph.D. IPM, who is the head of the Department of Civil and Environmental Engineering, Faculty of Engineering, Universitas Gadjah Mada. Ladies and gentlemen, I will give a brief rule before we start the sections. For these keynote speech sections, all of the keynote speakers will give a speech around 40 minutes. So in total, it should be 2 hours for 3 speakers. And after that, we will have a discussion sections for around 30 minutes. And yeah, so for the audience, for the participants, should you have any questions, please just drop it in the chat room during the presentations, and our committee will collect that questions and present it during the discussions. Or probably you also can just raise your hand and ask a questions directly to the presenters during the discussion sections. Well, let me now introduce the first keynote speakers, Professor Dr. Matthieu Kervyn. Professor Matthieu Kervyn is a lecturer in geomorphology and natural hazard within the Department of Geography of the Vrije University, Brussels. He holds a Master in Geography from the University Catholic de Leuven, Belgium, and a Ph.D. in Geology from Ghent University, Belgium. He currently leads research groups in volcanology, geomorphology, and natural hazard, and also supervising several PhD and postdoc researchers. Prof. Kervyn research combines observation from DM and remote sensing analysis with analog experiments and field observations. And the most interesting is all their case studies concentrates on the developing countries, mostly in Central Africa. All right, ladies and gentlemen, without further ado, I ask you all to give full attention for Professor Kervyn. So please, Prof. Kervyn, time is yours.
Okay, thank you very much, Mr. the Moderator, for the introduction. I'm very honored to have been invited to speak in your webinar. Maybe if you could allow me to share my screen, or if someone could load my presentations, that would help me. Because I'm currently not capable of sharing the screen. So as it has been, okay, thank you. As it has been introduced, I am developing research on different topics related to geohazards in developing countries, and indeed mostly in the context of African countries. So bear on me that most of the applications that I will illustrate today will be on some regions, mostly in the African rift systems, but I think there is a lot of analogies to be drawn from these places with the context in Indonesia. So what do we mean by geohazards? As most of you know, hazards can take different forms. They can be related to extreme weather events, floods, but they can also be related to the geological context. And here I've put some illustration at the bottom of landslides and recent volcanic eruptions that have taken place in Indonesia. So if we look at the definition of what hazards in general mean, it's a dangerous physical phenomena that release either energy or material, and that this phenomena can cause the direct loss of life or health problem, but also the loss of properties, of livelihoods, services, and disruption of the economic and social life of a community. And so in general, scientists, they want to understand these hazards, they want to forecast these hazards in order for them to be mitigated and managed in order to reduce this impact. And today I want to illustrate how Earth observations or remote sensing can help in doing that, and I will focus specifically on the understanding of specific geological hazards. Hazards, they are all over the world. You see here in one of these famous hazard maps, around the globe in green, we see mostly storms and cyclones affecting several oceanic regions of the world. But in red and orange, we see seismic activities, and also the red triangles are showing volcanic areas. So as we look, the regions where I am working here in the East African Rift, we have seismic activity and a lot of volcanoes. This is coming with topography, so we also deal with landslides, flash floods, and similar events. And obviously you will know that Indonesia is facing similar issues. Why do we care about hazards and disasters caused by hazards? Is that it has been shown that these hazards have been increasing over the last 50 years. Here on the upper left, you see the number of disasters that have been recorded by the global MDAT database. And you see that maybe initially we had just little records, but all the way till 2000s, we had an increasing number of disaster. In the last 20 years, it has leveled off because we have now a very complete, exhaustive records of these events. And we see that the dominant types of disasters remains the floods and the storms, but what is included in other types are typically the geological events, such as earthquakes, volcanic eruption, and landslides. And if we look in terms of continents, we see that actually the Asian continent is always on a yearly basis the continent that is hosting the largest number of disaster. And again, that number has been more or less constant over the last 20 years. What has been noticed also is that the number of fatalities has been decreasing because people have made quite good progress in saving the lives of people, but still more and more people are being affected by these disasters, including people that are displaced or that are losing their livelihoods. So we still have a long way to go to improve in mitigating the impact of these disasters. So when we talk about geohazards, what is it that scientists want to know? There are a few basic questions that I like to summarize in 4 question marks. It is the what, the where, the when, and the how. So what is it that we are facing? What type of hazardous process can take place in an area? But also, what are their characteristics? What is their magnitudes or their intensity range? So how big or intense they can be? And what are the controlling factors? Why do they happen in specific manner? How do they evolve? And so on. So like this morning, I was reading that they are evacuating half an island in the Caribbean. So the decisions to evacuate is based on an understanding of the evolution of such a crisis. We also want to know where these hazards can take place. And for that, we need to really understand how they happen. For example, on the lower left here is an example of a model for the lava flow emplacement on the volcano Mount Etna in Sicily. So we know that this is a fluid, it's flowing along the topography, and so it is possible to know where it will go. Whereas on the right, you have what we call the landslide susceptibility map. We can understand which factors are controlling the locations of landslides, the slopes, the type of geology, but also the soil and the amount of water in the soil. And all these factors combined can help us to identify where are the most likely locations of landslides in the future. Very important also, we want to understand when these things might happen, or in general, how often they might happen. For some natural hazard, it is possible to detect precursory signs, signals that shows that something is coming up. This is typically for weather forecast the case, but also for many volcanoes, there are indicators before the eruption start, whereas for other natural hazards, this is much less obvious, such as for seismic hazards. But still, on the long term, we can look at what we call recurrence interval or return periods, how frequently an event of a certain magnitude is coming back. And then we can build up graphs, such as you can see on the upper right here, where we look at the magnitude of specific event, here, for example, here, earthquakes magnitudes, and the annual exceedance probability. What is the chance that an event of a certain magnitude will happen on a yearly basis? And this is based on historical data sets where you need to have observations for quite a long time to be able to constrain such statistical indicators. It's not very useful to tell you if you have to evacuate or take specific measure in the next few days, but it is useful to know if a region has to be adapted on the long term to face specific hazards. And then, of course, we want to answer the how question and how to forecast. And so we want to understand as much as possible what are the processes that control the dynamics of hazards, how does it develop in time and over space? Are there interactions with other hazards? More and more we look at not single hazards, but complex situations where hazards interact with each other. When you have an earthquake generating tsunamis, generating landslides, blocking rivers, generating flash floods, and so further and so on. And for that, we need to know also what observations are useful, which monitoring systems have to be in place with which temporal and spatial frequency. And based on these observations, how can we feed in into models that tell us how the situation will evolve? We are already a long way in that directions when it comes to weather forecasts, but for geological process, we are still working on this. And this is definitely also being supported by advances in the techniques that we have to actually observe our natural environment. And we need more and more data. We need to characterize the evolution of our environments to understand how we are evolving towards hazardous situation. And we need to do that at different spatial and temporal scales. And for that, we have a range of techniques. We have the standard stations, such as weather stations, seismic stations. But nowadays, we work also with UAV drones systems to go and look at places that are remote, that are maybe dangerous to access. And then we have also satellite techniques that I will illustrate here. I don't explain what these figures show, but I will come back on these examples, which are showing displacements of the ground in several places. And so by combining these different observation and monitoring techniques, we can then evolve towards modeling and forecasting. And in there, remote sensing, so all the techniques that enables to observe, take observation from a distance are really key in feeding or modeling approaches. Earth observation has been used more and more in the recent decades for supporting crisis management cycles. I refer to that important paper in Science in 2016, which has shown that remote sensing is actually feeding in the different phases of the risk management cycles. From the start of a crisis that might arising, they are triggering the acquisition of urgent satellite image, they are being processed extremely rapidly during the crisis or directly after that, and that is supporting relief operations. There are different international systems that have been put in place in order for private companies, international national space agency to collaborate with each other to acquire rapidly satellite image, to provide them to teams that have the capacities to analyze them quickly in order to deliver them to the people on the ground, which are doing the rescue and relief operations. This is an overview of all the places where satellites remote sensing has been used to respond to different crises around the world. You see that it concerned hydrometeorological hazards, but also geophysical earthquakes, volcano and landslides. And these numbers have been increasing, and we've been really reaching stable numbers of crises being addressed every year, up to about 100 of these cases on a yearly basis. And what is important is also that the time for reaction has been decreasing. In maybe 10 years ago, we still needed 2 or 3 days for satellite products to be available after a crisis had started, whereas nowadays we are down to about a day and a half before actually useful remote sensing products can be used to respond to crisis. So this is becoming really an operational material, and in this case, it is to respond to crisis, mostly to look at where people have endured damages, where are the safe places, but also before the crisis is happening, there is more and more being done with satellites to look at the evolution of the situation. Just as an example, we are also dealing with new players in the field of Earth observations, whereas in the past we had mostly national space agencies launching satellites and producing satellite imagery. We have more and more now private companies that are developing their own satellite constellations, and the PlanetScope constellation is one of them, which is a series of satellites that are acquiring optical imagery with many sensors. That means that we can obtain actually on a daily basis an image of every place around the world. And this is very useful here, an example of Colombia, I think, where we see that over a couple of days, we have a change in the land cover, and that is clearly showing that we have several valleys that have been flooded, and where big flash floods have actually impacted on inhabited areas. So once you have these kinds of imageries, you can very quickly first understand what the process is that is responsible for this event, but also which areas have been impacted. Let me now focus on something that is closer to my research, specifically volcanoes. And I will later on delve on landslides. So volcanoes, they are multifaceted. They show different type of behavior once they evolve towards an eruption. They will typically emit some gas. They might increase in temperature, so they will emit heat, but they will also deform and generate some seismic activity. This is what the magma making its way to the surface can cause before the actual eruption starts. Seismic activity cannot be directly detected by Earth observations, but there are new techniques that enable us to monitor deformation, to monitor the emission of gas, especially sulfur SO2 gas. And then there is also different wavelengths where we can look at thermal emissions. And you see in this graph the number of detections, the number of images and sites where these kinds of processes have been detected. And again, we see that this has really picked up since the year 2000s, where we had new thermal sensors which enabled us to really monitor a large number of volcanoes on a daily basis, and we really can get these data in real time. Deformation is still something that is being developed, but more and more we actually can use this data for crisis management, and SO2 has also been improving very recently. So how does that work, a volcano? We have magma in a magmatic reservoir in the crust. this magma sometimes gets under pressure. It tries to find a way towards the surface that will come with topographic changes, with seismic signals. And then once the eruption starts, we have warm material at the surface emitting heat. We can have ash and gas, and we can have several flow processes going on along the topography. And each of these processes actually have a different signal, and they can be detected with different types of images. If you want to look at the deformation of the ground, you're not going to use the same type of Earth observation techniques than if you want to look at ash or gas emitted in the atmosphere, or if you're interested with the emplacement of lava flows. So here you can see, for example, when we talk about deformations, we will look at things that we call radar images, and we will try to detect the pre-eruptive deformation signals, how the deformation is taking place before and also maybe afterwards. But the deformation is very important before the eruption actually started. Whereas the heat, we will look into what we call the infrared signals, and there it's typically once the eruption has started that we have warm material at the surface that we can detect that and look, for example, how lava flows or lava domes are being in place. Whereas for gas, we look mostly in the ultraviolet and sometimes in the infrared, and we look at what is available, what kind of gas are in the atmosphere, in which concentration, and that can go from before the eruption, but typically as the eruption is ongoing, we will get more and more gas. So you see that the type of techniques, but also the timing of these different processes is different. Some illustrations. I've been working a lot on a region which is called the Virunga Volcanic Province at the border between DRC Congo and Rwanda. And we have there two major volcanoes. One is called Nyiragongo, which hosts a lava lake, and once in a while does a lava flow, but it's quite rare. And we have the other volcano called Nyamuradjira, where you can see all these black zones are actually pretty long lava flow, 10 to 15 kilometers long. And these lava flows are being emplaced every 2 or 3 years. So we have there quite a lot of interest to know when eruptions are coming up, where the lava flows are going, because there are large urban centers like here, Goma and Sake, which can be impacted by these eruptions. So I will illustrate what we can see from satellites. Look here, for example, this image from the EO-ALI sensors from 2012, and you see suddenly a very large signals on the upper left, northwest, northeast, sorry, and this is actually showing that we have an active lava flow being in place in that region, and that whole black area is very active. We see also that all along the flank of the volcano we have this brownish color, and that shows that the vegetation has been badly impacted also by some ash and gas being emitted by that new eruption. Whereas in the Nyiragongo crater, we do see actually the active lava lake. So here it's a combination of optical and thermal informations we get. From this, we can look also with time series, how these thermal emissions have been evolving through time. And this is for the same eruptions, which lasted actually for about 4 months. And we see that we can detect all the thermal pixels, how much they are being emitting. And we can derive the total discharge of lava that is being emitted on each satellite image. And this is with error bars, the signals that we are getting. You see that it's not very stable because the image, they can be affected by cloud cover, by gas. They can be taken under different orientations. But in general, we are able to document a peak of discharge at the start of the eruption and then a waning phase until the end of the eruption. This kind of information is very useful when you cannot really access the ground. You can tell when the eruption is dying off, but also based on these informations, we can simulate how intense is the lava flow and say something about where, how far the lava flow will reach. We feed that into lava flow models. The same thing applies for gas being emitted by that same eruption again. So this is a satellite image at a much coarser resolution. So the volcanic area is just here very small. We have a big part of Congo and Rwanda, Burundi being these two countries here. So we see we're at a continental scale. The resolution is of tens of kilometers. Sorry, there's a lot of background. Okay, so sorry, I think we have been cut. I hope I'm back. I was explaining that satellite imagery can also be used to monitor gas emissions. And here with these SO2 sensors, which are looking in the ultraviolet, how much gas is in the atmosphere, we can also look at time series and see how much SO2 is being emitted per unit of time. And again, follow up the process over time. Recently, we have had new sensors being sent from the Sentinel series of ESA, and we can get this at a higher spatial resolution and really derive the flux and follow up the process in real time. I want to illustrate that we can do also more detailed mapping from such satellite image for the same volcano. We have been excuse me, we have been interested in dating lava flows also. I want to show that also when the volcano is not active, we can learn a lot from satellite image. So typically we have different surface on the volcano, some which are fresh lava flows, some which are all lava flows already forested, some others are intermediates where they are covered with lichen. And when we look at big satellite image, typically in 1 pixels, we have a different types of surface within the same pixels. And we can use a technique which is called linear spectral mixing, where we tell the algorithm that within 1 pixels, we probably have surface of different spectra, and we want to decompose this to estimate what is the fraction of each spectra in a pixel. I illustrate here this with the spectra. If some of you are familiar with the wavelengths, typically the optical wavelengths are between 0.4 and 0.7. This is what we see with our eyes, but then we are in the infrared here beyond the 0.7 microns. So what we call the near infrared and then the shortwave infrared. And if we look at vegetations, we typically have little reflection in the optical, but we have a lot of reflections in the infrared, whereas for lava of different ages, this is quite different. And if we feed that into the algorithm, we are able for this same lava flow field of Nyoman to separate. So on the A image here, we have the fraction of vegetation. So the forests are white and the black are the fresh lava flow with no vegetation. And then for different age of lava flows, we can separate the all lava flows that are already quite covered with bushes, the intermediate lava flows that are covered with lichens, and the fresh lava flows that are still very bare. And using that, we have been able to decompose the surface covered of these different lava flows. We had the chance that we had many lava flows, so it was possible to look at which kind of surface, and we were able to show that the fraction of vegetations on different lava flows is directly proportional to the age. And so by doing that, we were able to actually provide some relative dating for some surface we didn't know exactly to which lava flows they belong. We could actually help to complement the geological mapping of that volcano. Of course, there are some outliers which can be explained by either some specific locations, or for example, when they're located next to a recent eruptive sites, they might be affected by gas or ash deposition. Want to illustrate another approach where we also look at the impact of volcanic eruption on the surface. I was working for my PhD on a volcano in North Tanzania called Oldun Nyolengai. It's nicely located in the East African Rift Valley. So normally we have a grass and bush vegetation around the volcano. I was lucky enough that it erupted moderately, let's say in 2007, and it deposited quite a significant amount of ash around the volcano. So on the upper right, you have the before the start of the eruption. On the lower left, you have the end of the eruption. And this is actually heavily, very well visible also on the satellite image. So we have the top of the volcano here. These are the steep flank, and then we are in the surrounding, and we see that the ash is going mostly towards the west and affecting this rather rugged topography. There are not so many people living there, but there are quite some small villages, people that were displaced. So we were interested to know how fast the vegetation would recover, for how long people would have to stay displaced. And we did that using time series of vegetation indices. This is a bit complex to explain, but these are change maps. So where we compare the vegetation between 2 years before the eruption and just before the eruption. And here we see not so much actual changes. You see that the values are very small. Then during the eruptions, the volcano is actually here, this black triangle, and we see these red patches. And this show actually the whole area where vegetation has been heavily destroyed. And this is being shown here in the graph, where before the eruptions, we have something quite stable. So we have the seasonal cycle, and then at the time of the eruptions, we have a drastic decrease of the vegetation cover. And then in the 5 years that follow the eruptions, we have a slight recovery. And this is what we see in the green here. From the time of the eruptions to 5 years later, we have actually a nice increase of vegetation. And using that and using different spectral indices, we were able to show how much time it took for the vegetations to recover. And that is depending on the amount of ash that is being deposited. And we can actually use this insight for future cases where ash is being impacting on the vegetation, and we are looking for other cases where this can be applied. Okay, so I've shown that volcanic eruptions can be used for detecting heat, for detecting gas, for detecting change in vegetation from impact of eruption. I want also to spend some time on showing that deformation of the ground is also something very important and where a lot of advances have been made. So ground deformations can come from multiple process, tectonic process, fracturing. These are famous fractures we have experienced in Kenya in 2018, eruption fractures, but also landslides. And these deformations, they can be extremely rapid, several meters per second, but they can be also extremely slow of a couple of millimeters per day or per year even. And so we need different types of technique. And one of these techniques is what we call synthetic apparature radar. This is an active sensor, which is sending a radar wavelength obliquely towards the surface and recording the amplitude and the phase of the signal that is coming back. This can be done at different wavelengths and at different spatial resolutions from 2 to 20 meter. We see that it gives images that looks like this. This is a volcano in Italy. It looks quite deformed because it's side looking, and so the topography is actually affected by distortions that needs to be corrected as you work on the image. But the interest is that this is an active sensor, and so you can acquire image at night with cloud cover. You are not depending on the sun to reach the surface. There has been more and more interest for this kind of techniques. This is an overview of the sensors that have been launched into the different wavelengths. We talk of L, C, and X bands. These are wavelengths of a couple to tens of centimeters. And you see that since 2010, there has been a range of sensors being sent. Maybe important to mention are the Sentinel-1A and 1B, which are from the ESA constellation and which are freely available online. And so these data are becoming more available, and so more and more people are developing capacities to analyze them. What can you do with this radar? You can look at the amplitude image and how the surface is looking like, but you can also use the phase signals to look at deformation. How does that work? Well, this is what we call SAR interferometry. What is important is that you get two images. So the satellite is passing by over a certain surface, you get the face back, and then the satellite is coming back later on, and from a similar point of view, but not the exact same place, it's again measuring the number of phase. And if there has been a displacement, then you get a phase shift between the two acquisition time. So the amplitude is one information, but the phase is another information. The phase as such, one phase image is not meaningful, but when you make a phase difference, then you can start looking at deformations. This is being shown here again, where you have two image acquisitions, amplitude and phase. And when you take the two phase, you can make a phase difference image. And this is starting to show some patterns. And these patterns, it might look like something like this. It's actually first being influenced by the topography. So you need to remove that topographic influence. So you need to have some information on the topography. And if you remove that topographic influence, then you get a patterns that will be related to the surface deformation. And the surface deformation, it doesn't have to be meter scale. Actually, it's depending on the wavelengths, but typically you will get information on 1/10 of the wavelength. So if you are using a wavelength of 4 or 5 centimeters, you can get down to a couple of millimeter displacement. This is showing fringes of deformation. So the full color from green to blue is one wavelength, so up to let's say 2 or 3 centimeters of deformation, and then you can do what we call unwrap. You can assume that one point is stable and start counting the phase for the full information on the deformation. So people have been able to illustrate deformation at volcanoes from seismic, from earthquakes, from landslides, of the order of millimeters to centimeter of deformation over time scales of weeks to months. So here an example of a large earthquake that affected Chile in 2016. You see that when we do the interferogram of this event, we get a lot of fringes, more than 30 fringes, and that shows that the displacement has been actually enormous. When we unwrap this, you see here the scale of deformation from minus 10 centimeters to plus 1.5 meter. So that means for one event, we have 1.5 meter of deformation. This is working best when the area is has no vegetation, no snow cover, and where the surface characteristics stay similar in between the two acquisitions. This can be done for one event, but this can be done also along time series and looking at much fainter deformations. This is a famous case of the North Anatolian fault systems in Turkey. Maybe you're aware that North Turkey is very prone to earthquakes, and this is due to a tectonic feature. And thanks to this kind of techniques, researchers have been able to show that this two blocks, so what comes in red here and what comes in yellow and blue here, are continuously moving relative to each other, and the discontinuity of these movements is exactly fitting with the fault, so that there are continuous accumulation of stress along this fault, and this is a possibility to calculate this stress and say something about the chance or the magnitude of future earthquakes. For that, you need actually long time series and accumulation of many data sets. We have done that also for the same volcano Nyoman in Congo, where we've been looking at vertical and horizontal deformations prior and during eruptions. You see the signals here on the graph below, and you see the maps actually that enables to detect where the eruptions will actually occur. So once you go towards the eruption periods, you see that the deformation is accumulating towards this point A here, and just at the time the eruption started, you actually have a deflation phase that follow an inflation. So nowadays we actually have access to this image almost in real time. So after a couple of hours, you are able to develop these kind of maps, and you are able to interpret them and say something about how the eruption will evolve. Just over the last couple of weeks, we had such a sequence in West Iceland where the deformation was ongoing, where they had more and more earthquakes, and the eruption finally got to the surface 10 days ago. The same technique can actually also be used to detect other type of ground movements. These are some slides coming from a PhD defense of last week of one of my PhD students. He has been monitoring the displacement of what he calls slow-moving landslides also in the Congo regions. So many landslides are shallow and they move fast. For that, we need just change analysis before and after image to see where the vegetation has been impacted. But you have also other geological features where the movement is slow and they're typically deeper, and where you can have deformation of a couple of meters to a couple of centimeters per year. And there again, we need some more subtle satellite techniques to actually detect this deformation. So again, he has been using, on the one hand, radar images, on the other hand, optical images to look at this deformation. So thanks to the radar images, he can use the phase component and do the interferogram, what I've just shown, but also he can use the amplitude image and look at the deformation in amplitude. So this is a bit more like what we would do with our normal eyes. We look at how the surface look like at different time steps and whether there are any movement. And if there are movements, we have now techniques which are called pixel offset tracking, looking at really movements of a different pixel within the image to detect this deformation. I will explain that a bit more further. What we do is that we have a series of images acquired through time under different geometries, because the radar is oblique looking, so it takes one image looking on one side when going from north to south, and on the other side going from south to north. So we have two time series, and we will compare the deformations between all the pairs of the time series, so that we have actually redundant informations and we can constrain the deformation as much as possible. And the goal is actually to look at the cumulated displacement over time in between all these images. And this is how we can evolve towards one time series where we will have both the vertical and the horizontal displacement. So we've done that on a big landslide, which is called the Ikoma landslides. It's in South Kivu in Congo. We have had some field terrains where we've used drone image acquisitions to actually have some very detailed topography at some time step. But of course, we cannot be on the ground all the time. UAV technology, I mean, you need to be very close by. So it's still quite intense in fieldwork. And so we've complemented that with this satellite image. And the two actually are very highly complementary. So I hope you can see this small movie. This is actually the radar amplitude image of that landslide over a series of years. And maybe it's not so clear, but what we are looking at is this central part of the image where if you look long enough, you see that this is actually changing. And especially here, we see that something is falling towards the southeast. And this is actually, this whole body is the landslide. It is about 17 hectares, 800 meter long, 400 meter large, and has been mostly moving since 2016. The activity was mostly up here, very visible, but actually when looking at satellite image, we saw that the whole body downward from it is also moving. And we're talking about displacements of 5 to 10 meter over 1 year. This is how it looks like on drone images. This is the first acquisition of drone we had. We see already the landslide very clearly, what we call the head. So that part is very clearly a landslide, but actually the whole body underneath has shown to be moving. When we take other drone images about 9 months later, we see that there was actually a significant change, and then later on the second time periods show less changes. You see that thanks to drone, we have topographic informations at a very detailed scale, about 10 centimeter resolution. So we see much better than what I could show with the radar amplitude, but our temporal resolution is much weaker. We had to go there, we had to take the images. Sometimes you're unlucky, the weather is not good, you cannot fly, and so on. So the two techniques are actually highly complementary. But I would advise, if you are monitoring landslides, the drone technology is becoming very, very efficient and not so expensive anymore. And so to illustrate,
sorry,
yes,
your time is 5 minutes left. Sorry about that. Just for the information.
Yes,
your time is 5 minutes left. Yeah.
No problem. I'm concluding. So to finish up on this example of landslides, when I look back at this amplitude image, so this small video of the radar image, with the naked eye, it's not so clear, but when we use the algorithm of pixel offset tracking, we do get this kind of map here on the left. So where over the entire landslides, we get arrows of displacements and velocity of displacements. And you see here, this is meter per year. We are going from 0 displacements on the outskirts of the landslide up to something that is over 8 meter per year on average. And thanks to the many images that we have from this radar sensor, we actually have a very good temporal resolution. And this is on the upper graph here. We have the cumulated horizontal displacement over time. This is a time series over 4 years. And we see that we had a major phase of acceleration here in 2016, and then another one at the end of 2018. From that, we can derive the velocity of displacement here in the red curve in the central. Put again, and then we can start looking about what are the causes for that. We've been looking at earthquakes occurring in the region, here the yellow bar, but we don't see much correlation. So it seems that the tectonic triggering is not so important, but we've also been considering rainfall. This is the gray shading here. We have also a station on the ground, and we have been modeling how much water pressure there is in the soil. This is here the blue curve in the central graph. And we do see some kind of correlation between the rising of pore water pressure in the soils with the acceleration of the landslide movement. It's not working all the time, but when we have high pore water pressure, we typically have an acceleration of the movement. This is well known that poor water pressure is important in driving landslides. We were actually quite surprised that for such a deep landslides, the landslide was reacting actually very quickly to intense rainfall. And then finally, another way to look at that is what we have discussed as the SAR interferometry using radar signal. The radar is useful when the deformation is much smaller, not in meter per year, but rather in centimeter per year. That we would not be able to see with the radar amplitude image. And so we have been using that in a city environment where we have a lot of buildings that reflect the radar signal. And we've been able to show that in that city of Bukavu, we have in the less nice neighborhoods, the slump neighborhoods, we have actually deformations of a couple of about tens of centimeters per year, and with some area where no signal is detected because they move too quickly. So you see that we can combine either for fast moving features, we can combine optical or radar image and doing pixel offset tracking. For slow moving features, radar interferometry is still very useful. Just we do still struggle with a challenge for forested areas. And then I come to my conclusions. I just want to point out that in this talk, I've been discussing different techniques that are useful to characterize the hazards and a little bit the impact of these hazards on people. But let's keep in mind that the risk is actually not only the hazards, but also who is exposed to the hazards, how vulnerable the people are, and what capacity they have to react to this. And for all these components, actually, Earth observations can be useful. We have done other studies where we are looking at population distributions, type of buildings, and impact on people from different types of geohazards. So combining all these approach and using Earth observation with all its capability can be very useful. And we, in our projects, we typically combine that with a lot of outreach, also working with the local stakeholders, the local communities. We have been issuing policy brief to return the results of the research to local people, using posters for educations, installing local stations. And we have also started working with new ways of interacting with communities, such as serious games, trying to do risk management simulations with local communities. We have used also citizens as scientists, collecting observation on a daily basis on how the situation in their environment is changing. And we've been showing that this helps to actually validate things that we observe with satellite observations. So as a conclusions, I think the field of Earth's observations for natural hazards has been evolving immensely over the last decades. It has now proven that it has a great potential for actually supporting risk management in real time. It can be used to detect triggering or onset of hazardous events. It's now being really used as input for early warning systems. It can be combined with stations on the ground or with other type of observations like citizen science to help the response during disaster phases. But more and more we see that satellite image, it's not only to observe what happened at the surface, but we can quantify, we can characterize, and we can use that in risk modeling. And so let's keep in mind that satellite image, they are not just photographies of the surface, but there are multi types of sensors working in different wavelengths at different spatial and temporal resolution. And it's by combining all of these that we get more insight on the process we are interested with. Thank you very much for your attention, and I'm very open for questions now or during the discussion session.
All right. Thank you very much, Prof. Matthieu. So yeah, let me conclude. So based on the Prof. Matthieu synthesis, we can conclude that monitoring hazard can be done with a range of techniques, and remote sensing is really good approach to do that with a lot of advantages. And remote sensing also powerful to detect both emissions, active volcanoes, also eruption impact on vegetations, and also ground deformations. And also it could be potentially compared with radar. thank you very much. So on behalf of the committee, I would like to thank you for the excellent presentations. And let now give a big applause to Prof. Dr. Matthieu Kervyn. Thank you very much. Well, ladies and gentlemen and the participants, yeah, if you have any questions from the Prof. Matthieu talks, you can just drop your questions in the chat box in this Zoom. So our committee will collect it and we will discuss it in the discussion sections. And now let's enjoy the second speaker, Prof. Dr. Bernard Aris Marfai, S.Si, M.Sc, who is the head of the Indonesian Geospatial Information Agency. Yeah, in 2008, Prof. Aris graduated magna cum laude and received his doctoral degree in the geography from Justus Liebig Universität, Gießen, Germany, in 2 years. And yeah, in just 2 years and 8 months, that's very fast. He also completed an M.Sc in Earth System Analysis at International Institute for the Geoinformation Science and Earth Observations in the Netherlands from 2001 to 2003. In September 2013, at the age of 37, Prof. Aris assumed his professorships at Universitas Gadjah Mada. So that's very young. He is a highly active member of the Center for Natural Resources and Development. Prof. Aris also have a lot of programs and research experience from 2015 to 2021. And also Prof. Aris has produced over 220 publications, and up to June 2020, he has supervised 25 Ph.D. students from Indonesia and abroad as either the first or co-promoter, and 115 master students and 35 bachelor students. Well, without further ado, let us now welcome the head of Indonesian Geospatial Information Agency. Please, Prof. Aris Marfai, time is yours.
Thank you, Mr. Moderator. First of all, I would like to thank for the organization committee who inviting us to join of this very valuable international webinar on the 71st World Meteorological Day. And it is my pleasure always to come back again and again to the STMKG, as always, at least 1 a year. I realized that we have a communication and we have some occasion with STMKG, and it is very good to maintain the cooperations. Previously, I was in UGM, so we are really very close cooperation and some things, for example, on the education, research, and also the services. So today we have the very good occasion, and let me start to present my topics, and later on we can have the discussion. First, the Honorable Pak Nyoman Sukanta, thanks very much, Pak Nyoman, for inviting us. Also, the speakers, my colleagues, Professor Faisal Fathani, and also Professor Matthieu Kervyn. Let me share my presentation first. I hope everybody can see it.
Yeah, that's clear.
Okay, great. The thing is only just 1 minute before we start, I crashed my PPT. So some of the images could not be proper, what you call it, shown on the screen, probably. But let me see what can we manage later on. Today I would like to present about the, as mentioned by the committee, about the hydrometeorological hazards. And now, but I try to link with the utilization of geospatial information. Since now I'm has the responsibility to chairman the Geospatial Information Agency of Indonesia. So I moved from the university to the national agencies for geospatial information. Therefore, in our agency, our task or our duty is to provide and to maintain, as well as to monitor the geospatial information and data, which can be used and to deliver to other agencies for development purposes. One of them is actually also in terms of the disaster management. So we provide the geospatial data for disaster risk management. As we may also aware, all of you also aware that some Indonesian disasters almost year by year are increasing, and most of them are caused by what we call hydrometeorological disaster. So some of the disasters actually happen because of the cooperation between the climates, water, and also the terrains. And some of them, for example, leading to what we call landslide, flooding, coastal inundation, etc., and so on. And this is the most what you call it happening disaster in Indonesia since last 5 years, 10 years, I think. So beside this, as we may also aware that natural disasters, especially the hydrological event, are very latent in Indonesia. Why? Because many people in Indonesia actually reside in the areas of the vulnerable. We have 34 provinces, more than 500 cities and districts, 500 cities and region, and also more than 70,000 districts, etc., and so on. So you can imagine how large we are and how vulnerable we are to kind of the disaster. If you have a look at this data, for example, some of the hydrological events are dominant in the term of the losses and damage. For example, the Jakarta floods in 2007, we have loss and damage more than 5,000 billion rupiah, and also Wasior flash flood, for example, more than 200 billion rupiah, and the North Sulawesi flash flood more than 1,400 billion rupiah. So this is actually a very huge amount, and this is beyond the intangible loss and damage as well. So, for example, victims, social network destruction, environmental destruction, etc., and so on. So actually, the many things can destroy due to the disaster as well as due to this hydrometeorological event. This is the example how the impact of the hydrometeorological hazard. This area is on the coastal area of Central Java. That was villages. And nowadays we cannot use this village anymore. So this village is abandoned due to the permanent inundation. Why it's become this like this? Actually, because of the dynamic of the coastal area, but also the increasing of the what you call it, the water level from the sea, or sea level rising, and become permanent inundation in that area. So this is also another example. How it was, for example, we lost the area in the 3 years around the 100 meter due to the sea level rising as well as the erosion, coastal erosion. And another data also told us that, for example, in the increasing sea level rise in the future, so compared to several countries, Indonesia with only 60 centimeter, we will lose 34,000 kilometers square of land. So actually quite a huge land. And then this also suffer impact on the ecosystem as well. This data is to prove us on the last 10 years, for example, from 2000 up to 2014, we can see clearly this is on the mean sea level that was in the 80 centimeter around this area, around this area. But then during the last 10 years, they are increasing up to 140 centimeter. This is the highest sea level, the mean sea level. And this is for the highest sea level as well. We have two groups different, previously 150, and nowadays in the last 5 years, we have 200. So this start from 2000 up to 2014. So there is also happen on the low low mean sea levels, low sea level, which is we have two groups as well. So it's mean that on the last 10 years, due to the climate change, we have more sea level rise in that area, and this is causing what we call it coastal inundation, flooding in the city, urban coastal areas, etc., and so on. And so what we can do then as the geospatial information agencies, if you have looked, this is the circle of the disaster risk reduction program. So priorities in disaster risk reduction management, as this is present day framework 2015 said, among those, actually, the geospatial information will have important rules for activities of the disaster risk reduction management program. For example, on the prevention, on the awareness, on the preparedness, as well as on the early warning system. One of the important thing is actually geospatial information, how we can support the geospatial information to do the risk analysis, how can we support the geospatial information for disaster mitigation and the whole aspect. This is what does the PIG do, which is the disaster risk reduction by using geospatial information and services. PIG contribute to some support disaster mapping, for example. I will show you some of the example of the disaster mapping. We are supporting also the mitigation and response, for example, to provide the map of the logistic needed, the map of the distribution of the logistic, and so on, as well as the disaster risk reduction program. So in each step, for example, in the preparedness, emergency, rehabilitation, and the prevention, in each step, we need the geospatial information. I will start from the base geospatial information in hydrological hazard and disaster risk reduction. In our agency, actually, we have two main tasks, which is to provide what we call it base geospatial informations. And the second is to provide the thematic geospatial information. The base geospatial information is the consists of what we call it peta rupa bumi, which is consists of the information of coastline, information of infrastructures, information of utilization, information of land use, information of contours or elevation, information of the boundaries, district boundaries, administrative boundaries, information of the toponymy. So this is actually the basic map that we should provide for government, for local government, for people, for private sector, etc., and so on. So this year, just to inform you, we should start on the large scale, which is 5,000 scale for whole Indonesian. So this is really big project, and according to the RPCM, we have the mandate to finish this in 5 years, so up to 2025. So we are now incorporating with the BUMN or the state-owned enterprise to conduct the mapping on the whole Indonesia. You can imagine very large of area. Some of the information in the base map we can use to help to support the disaster risk reduction. For example, this is the course data and episodic data, which is the data that conducted by the PIG in the last 5 years, and consists of the, for example, the GPS stations, and based on this we can see the movement, very slow movement of our area. For example, in the GPS, the blue line, they move up to 15 millimeter per year, etc. and so on. So we are recording this data year by year, actually. The second thing, our agencies also conduct what we call tide gauge measurement, which is data from online tide gauge station will be useful for supporting several activities of disaster risk reduction, such as for tsunami early warning system. And we supply always time by time to the PMKG our tide gauge data, and then PMKG analyze the data, cooking the data to be an information for the society, information from the government in terms of the disaster risk reduction. So we are in the kitchen, provide the data, and then PMKG cook the data and provide the information for the society. That was the rule actually. So in the pictures, we can see our station. There is states on the orange, Stasiun Pengamatan Pasang Surut Tsunami Pelabuhan Pantoloan. It's mean this is the station for tide gauge and tsunami measurement monitored by PIG, by our agency. Other thing, actually, the tidal gauge can be used as well for risk assessment for potential impact of several coastal hazards. For example, on sea level rise, as I mentioned before, the coastal flooding, coastal abrasion, erosion, as well as we can use for the mapping on the coastal area, the dynamic of the coastal area, how the change of the coastal area, etc., post event, for example, etc., and so on. This is just to give the illustration how our contribution to INA TWIs. Actually, this is also the cooperation with PMKG, with the PNPP, etc., and so on, with PPPT, etc., and so on. So this is the mechanism from the PIG GPS course and PIG tide gauge. From the sensor, we send to the data logger, and the data logger can send to the CPU, and then through the satellite, internet, and then we can get the near real information and processing and analysis centers, not only in PIG actually. After the processing, we kick out the data to PMKG, we kick out the data to PPPT to further analysis, as further analysis is tasked by the PMKG, for example. That was actually the basic of our duty in the PIG based on the base information, geospatial information. Second thing is, I mentioned before, the thematic geospatial information, and especially today we'll see how we implemented this in the hydrological hazard and disaster risk reduction. Thematic, it's mean depend on the topics, depend on the requirement, depend on the request from other agencies, from the government, from the society, from the local government, etc., and so on. For example, the PIG disaster mapping held by in a term of the prevention and mitigation. For example, we conduct the flood hazard stability map in the base of our regulation 2015. We conduct this year by years. And then the multi-hazard or multi-susceptibility map, land and forest fire disaster standard as well. So, and during the emergency response, we do the rapid mapping standard for disaster rapid mapping unit, rapid mapping for disaster emergency response, and so on. And then during the rehabilitation process, we develop the thematic map, for example, the land use map, morphometry map, land system map. We are now finishing the land system for whole Indonesia on the scale 25,000. And this year we are finishing. We will finish the East Java, Bali, Papua, and some part of NTT and TP. And then also the fundamental geospatial data, for example, as I mentioned, topographic map or base map scale up to 5,000. And then data position, geodynamic, mean sea level, geoid, apa namanya, geoid, as well as the gaya berat, etc., and so on. There is another example how we can implement the data for thematic hydrological hazard. For example, the coastal subsidence, coastal flooding, and inundation in Indonesia. We have conducted the study On the landscape system derived from the GPS scores, as I mentioned, the GPS score is part of our task. So we collect, we now have around 64 points for the course stations. But we do also the GPS survey, for example, as well as the INSAR, the radar, etc., and so on. So based on this, for example, we implement on the whole of Java for tidal flood, and then for surface water degradation, infrastructure damages, etc., and so on. So this is part of our activities related to the thematic geospatial agencies for hydrological hazard. And this is just, for example, how we conduct the MOU, for example, between PIG, the Minister of Public Work, as well as the STMKG on the flood hazard map development. So we are conducting this on the selected of flood hazard location based on the Index Resiko Bencana Indonesia. And it has been implemented since 2006 with coverage area more than 266 cities. So actually this also one of the big activity that we have so far in terms of the disaster management and mitigation action. And this is another multi-map. If we have looked the types of the hazard, earthquake, tsunami, volcano, flood, landslide, drought, we can see that the 50% of this actually related to the hydrological hazard, which is flood, landslide, and drought. So we do this geographic assessment and landscape analysis to evaluate the susceptibility of any areas, and using, for example, what we call it analytical hierarchy process. So this is also the thing that we have done so far. Beside this, related to the hydrological hazards, we do also the mapping of the forest fire, which is one of the hot issues in Indonesia year by year, is the forest fire. So we do also the mapping of the forest fires in the cooperation with the Minister of the Forestry. Also, another activities of the rapid mapping, for example, on the post-rapid event assessment affected on the fast flood and landslide. Just recently in Bogor, on the beginning of 2020, for example, this is just our neighbor because our office is located in Bogor. So we use the rapid mapping, uses unmanned aerial vehicle, and combining by field surveys to have more detail in a scale of 3,000 up to 5,000. So this is really very huge. We cover some part area in Bogor agencies of the affected area due to the flash flood and landslide. And we delivered this information, we finished already, this is in 2020, to the BNPB as well as to the local government. And they use this map to do the management of the disaster, for example, the relief as well as the transfer logistic, etc., and so on. So another thing, we do also the acquisition data for the post-disaster, for example, using the high-resolution satellite images, the land use map, land system map, morphometric maps, and so on. So we combine all this data. So for those who needed the data, for example, you just post the request to the PIG and we will deliver the data, especially for research or for STMKG, for example, or for analysis for PMKG, etc., and so on. And last but not least, actually we provide as well in our website on the tanahair.indonesia.go.id all those data, so you can access the data freely. In some part, you can use as services, you cannot download it, but some part you can download it. So this is the geospatial data related of the disaster, not only on this particular location, but for whole Indonesia. We have, for example, the topographic maps, the base map, some of the thematic area. The one that we show you in the screen is the for Palu and Donggala earthquake, for example. So as closing, the geospatial data and information actually important, needed at every stage of the disaster reduction management. As we know, that in every stages, in every stage, we need the data, not only the tabular data, not only the data related to the victim, related to the loss, but also the data related to the location, what we call the spatial data. So therefore, now we are trying to strengthen our capability, for example, on the systematic disaster-related research, on the detailed and accurate geospatial information. As I mentioned, we are now finishing 5,000 skill of the basic map, and then also we have the hazard-based spatial planning. Though actually our duty not really related to the disaster, we have the part of the unit, we have the part of our echelon 2, the echelon 2, we have the what you call it, pemetaan thematic of the thematic mapping. One of the thematic mapping is on the disaster. But also we can support the reliable early warning system by developing the system, since we have also the unit or deputy on infrastructure information geospatial. So the people there are responsible for rapid geospatial data sharing, for management data, geospatial data, etc. and so on. So we should do also the regular exercise for dealing with disaster, especially also ask how we can support the exercise by providing the good map, the good geospatial data, etc. and so on. Also nowadays we have the communication, for example, with the insurance company, how we deal with the disaster-related insurance and the compensation, etc. and so on. So this is also the part of the important thing that can support related to the hydrological disaster. This is just to show you some of my book actually, but unfortunately we cannot show the picture here. The empty space is actually the cover of the book. This is the first book in the total of the 3 books, and the first part of 3. The first book shows the different aspect of the climate adaptation, joint initiative, the city Rotterdam, the New York, and Jakarta. But anyway, you can find it as well in the internet, what we call it, the connecting Delta cities, about the global coastal city and the future challenge. This is the second book. Again, very unfortunate we cannot see the pictures, but this is also related to how we can combine Rotterdam, New York, Jakarta, London, New Orleans, Hong Kong, Tokyo, and Ho Chi Minh cities. Me myself is part of the author as well on the second book, and this is the third book. Very pity we cannot see the cover area. So I think that was the end of the presentation, and thank you very much. Looking forward to have the discussion with you all. Thank you. Time back to you, moderator.
All right. Thank you very much, Prof. Aris, Marfai, for such a great presentations. So we can conclude that geospatial mapping in a very high resolutions and the observation data, such as a TechGauge and others, is really important to reduction for the natural hazard impacts. And yeah, for the audience now, please give applause to Prof. Aris Marfai for the great talks about this. Yeah, thank you very much. All right, so again, from the audience and from the audience and other, if you have any question, just hold in. You can just write it down in the chat box in the Zoom, and our committee will collect it and we will bring it in the discussion sessions. Well, so we will move to the next speaker, our last speaker, who is Professor Teguh Faisal Fathani, STMT, Ph.D, IPM. Yeah, Professor Teguh Faisal Fathani is a professor of geotechnical engineering at the Universitas Gadjah Mada, Faculty of Engineering, and he earned his bachelor and master degree in civil engineering, UGM. And for the doctorate, he graduated in the geotechnical engineering at the Tokyo University of Agriculture and Technology in 2005. He continued his postdoctoral research at the Ehime University in 2010 and the University of Iowa, USA from 2013 to 2014. And currently, Professor Fathani serves as several positions. Professor Fathani serves for the director of the UGM Center for the excellence and innovations in the disaster technology, or Gamma Inatech. And also Professor Fathani served as a vice president of the international consortium on the geo-disaster reductions from 2012 to 2021. Professor Fathani also held a vice president of the international consortiums on landslides 2021 to 2023. He also head of the Department of Civil and Environmental Engineering in the UGM, and also the director of strengthening Indonesian resilience reducing risk from the disaster. And in 2018, Prof. Fathani was appointed as adjunct professor of UNESCO chair on the geo-environmental disaster reductions until 2023, and he also has several patents on the landslide applications. Yeah, so that's very great background from the Professor Fathani. Well, all right, so without further ado, let us now welcome Professor Teguh Faisal Fathani, STMT Ph.D. IPM, for the presentations. Please, Professor, time is yours.
Thank you very much, Mr. Chairman. Can you hear me?
Yeah, we can hear you.
Okay, good. So thank you very much first to Pak Nyoman. Thank you for this opportunity and invitation, and to Professor Matthieu, Kervyn, and also my colleagues, Professor Aris, Marfai. So it's very great for me to see your excellent presentation. So please allow me to share my screen. Yeah. Can you see that?
Yeah, perfect. We can see that, Prof. Thank you.
Okay, thank you. So today I would like to speak a little bit broad, yeah, not only for landslide, but I try to also introduce some approach for multimodal sediment-related disaster mitigations. So it means landslide, flood, past floods, debris flows. So we're going to discuss that, and also how we have a socio-technological approach for disaster mitigation. Yeah. And now I'm working in Gajah Mada University. I'm the director for Center of Excellence of Tech for Disaster Mitigation and Technological Innovations. And also I one of the founding fathers of international Yeah. I also the founding father for consortium on geodisaster with 60 members from 60 countries. So starting from the beginning of this year, I replaced the position of Professor Dwi Korita Karnawati to be the Vice President of International Consortium on Landslides, representing ASEAN regions. So this is my outline of presentation. I will discuss first about geo-environmental disaster on Earth, and then disaster risk management in sustainable development goals, and how to shift the paradigm to focus on disaster risk reduction. And then introduce also one of our ongoing effort in establishing the international standard for multi-disaster early warning system, also in cooperation with BNPB and also Indonesian Standardization Agency. And finally, I will discuss about technological innovation and mitigation procedure for disasters. So we know that Indonesia is located at the Ring of Fire, starting from New Zealand, Pacific Islands, and then the east part of Indonesia, going up to Philippines, Japan, and go to the west coast of American continent. And near at the plate boundaries, we have a lot of volcanoes there. And of course, when we look at the distribution of the shallow earthquakes, the location of the epicenter is located near the plate boundaries. It means that our country is very prone for earthquake and tsunami, volcanic eruption, and also other multimodal sediment disasters. Then this is the distribution of natural hazard on Earth, earthquake, and then tsunami, volcanic eruptions. White colors show that less impact on the human casualties, but the red colors mean a lot of victims during the occurrence of disasters. So yes, it is. This is our country now in Indonesia. It's very crowded there. And what kind of disaster we have? We have a flood. This flood is just located in the capital of our country, and then this is the landslide in Semarang, Central Java, lahar flow due to Merapi eruptions, drought in the Gunung Kidul area, and also earthquake in NTB. As you may know that if we discuss about the national development plans in all over the world, we need to be consistent and also should focus on the achievement of sustainable development goals. We have 70 goals, while 10 of the goals strongly related to disaster risk management. Usually we know about number 11, sustainable cities and community, but we work a lot of overlapping area, no poverty, no hunger, no good health, etc. It's very close to disaster risk reduction. So among 17 SDGs, 10 of it strongly related to disasters. That's why we need to establish the role of disaster risk reduction as a core development strategies. So this is just to point out that what we discussed today is very important, and also it can direct our national development strategy as well. What is going on is we don't put any attention on disaster risk reductions. As you may see that we need to focus on reducing the exposure and vulnerability of the poor to disaster, and also we need to promote and integrate disaster risk reduction into sustainable development and investment decision making. We need to invest something in order to get the result in the next day. If we do nothing, then the global average annual loss from disasters, it will go from $260 billion in 2015 when Sendai framework was established, to nearly twice by 2030. This is one example that how that disaster cause the people fall into poverty in some selected area. For example, in Pakistan, after the flood in 2010, more than 35% of the population falls into poverty. And also in Philippines, in Cyclone Hainan, 2013, more than 23% of the population falls into poverty. So this is very important statement here by UNESCO 2017. Disasters can derail hard-earned development plans and progress. That's very important, especially in developing countries like Indonesia. So this is the condition of Indonesia. This map show the distribution of earthquake epicenters all over Indonesia. So we have to put attention on the earthquake disaster as well. It is located near the plate boundaries. And then we have about 126 active volcanoes in Indonesia. So it's mean that we have a fertile soil and good for plantation, but also on the other hand, we have a problem with multimodal sediment disasters. So I took this one particular slide from the slide presented by Professor Di Corita in 2015 in Sendai. At the time, she asked one very important question. So many disaster research, but why still many socio-economical loss? Why? So in this case, we need to apply research, science, and technology for the life survivability. So in short, we need to put science into practice. So that's also one of the topic that I'm going to highlight today. Prof. Aris just now showed the disaster management circle, so I would like to see from other side. So we pushed a lot just after disaster happens or occurs. Yeah. So here, we work a lot here in emergency response state, but we put less attention on normal or disaster risk reduction stage. And you can see the media, the lower part. So media exposure also, we got a lot of exposure during or just after the disaster, not before. So after the disaster, I got a lot of contacts. I received a lot of contacts from media, radio, national television, with the same question, why? Why this happens? I say that why? Why you contact me now, not before? Yeah. So it's kind of like a paradigm that we need to shift this one. So this is the most important slide in my discussion today. We try to shift the paradigms. The left side, it's what is going on now. So this is our current condition. We put less attention on reduction and readiness, and we put a lot of attention on response and recovery also just so. Yeah. So what is the meaning by resilience or country resilience or community resilience? In the way that we could manage these four components of reduction, readiness, response, and recovery in a proportional way. So the overlapping in the middle, that's what we call as the resilience. Yeah, but we have a big problem here because we cannot. So when we invest, like I said before, we need to invest something for disaster reduction. We are not going to see the result just like human. You know, when we invest something, we need to get the benefit as soon as possible. That's not gonna happen. We need to wait longer time to see the result. Maybe our children, grandchildren will get the benefit of our investment nowadays. So how to shift the paradigm? We need to shift our mindset from response to reduction. We need to change the focus from hazard to the risk, and also from single mandates to integrated planning, involving a lot of stakeholders, many stakeholders to work on this integrated planning. And the centralized we try to increase the local government and community capacity so that they can save themselves during the disasters. This is what we write in the books in KPDT 2 years ago. So this is the problem of underlying risk factors, socio-economical technical problems. We have, so this is the real problem we have. We have poor community awareness and preparedness. We have limited access to the information, limited capacity of local community, government, and university or NGO, and then socio-economical political condition also, that's also one of the obstacles, because once we have a plan to conduct, for example, the socialization involving some local governments body and also the NGO, the community, we cannot do that before the election. Yeah, we need to do it after, because the situation is not so good at that time. But you know, disaster can happen anytime. Yeah, not waiting until the election finish. And then we have also the problem with uncontrolled land use management, and also lack of technological innovation for disaster mitigation, especially for developing countries like Indonesia, and also lack of socio-entrepreneurial approach in disaster risk reduction. We need to integrate our planning. Yeah, if we fail to plan, then we will plan to fail. Yeah, so that's key. So we need to involve so many disciplines here: social welfare, health, research and education, emergency management, policy, law enforcement, economic, infrastructure, and technological innovation. So all of this. So we need to work together, because disaster is everybody business. Do not focus on the business only, but everybody. Yeah, it's our concern. So because I talk in front of the student from STMKG, I believe that there is one question: what can we do as the academia or as the student, university student, to support this disaster risk reduction initiative? There are several ways. This is, for example, what we call as the hybrid socio-technical approach. We have the technical system, the upper part here, and we have the social system here. And we, in higher education, has the role to combine this strength, technical systems, and then social system to push it to reach what we call as the hybrid socio-technical system. So honestly, it was initiated by Professor Dwi Korita Karnawati at the times, maybe 10 years ago, and now so many young researchers, students work on this direction. So if we are going to develop a strategy for disaster risk management, what should we do? We need to start step by step. Yeah. The first step is to provide appropriate investigation and information. Professor Aris and also Professor Aris and Professor Matthieu, they discussed also so many about the disaster condition, hazard, area, risk map. We need to do a good investigation and good information. And then after we get all of this information, we need to provide an appropriate countermeasures and technology. That's my part because I come from civil and environmental engineering department. We need to design a good mitigation work, and also in case that we cannot, we don't have enough time or enough money to do the mitigation work, it's quite expensive, then we can focus on the early warning systems. Yeah. And then the third step that we try to promote the education and training, public education, training, evacuation drill. And finally, what we're going to achieve is a society resilience. So today I have no time to describe all of this, but some of the important role like early warning system I will highlight first. Yeah, early warning system. So when we are going to promote a concept into a national standard or even in international standard, we have to do a lot of research on that. More than 10 years, we do a lot of research, publish a lot of articles, and then finally we believe that this concept is good, and then we push it to be a national standard and international standard. So this one I was invited to talk in Geneva in the UNICE and ISO meeting in Geneva, and also we are invited in APEC meeting in Chile to discuss about our initiative in standardize the early warning system in the world. And now we are working on 5 ISO standard. The first one has been published in 2018. It was ISO of landslide early warning systems. And the second one was published last year, ISO guideline for multi-disaster early warning system. And now under Pak Sadli, Deputy Sadli, and also Pak Rahmat as the director, and also Bu Eniza of STMKG, we promote the ISO for tsunami early warning system. Yeah, that's hopefully this year we could publish this the third ISO standard coming from Indonesia. So this ISO were the first ISOs drafted by developing countries. Usually it's drafted by developed countries. All of the ISO standard we have, ISO standard for 14,000 series, 9,000 series, so it come from the developed countries. So this is the first one. And then the left side we have the national standard, the right side we have the international standard that has been published, and this is drafted by Indonesian in cooperation of BNPB, BMKG, standardization national body, and also UGM, yeah, Gajah Mada University. What is inside that standard? So we put that it's difficult to relocate the community, so we need to increase the preparedness, the awareness of community to implement the early warning system. So we try to, as the objective, we try to integrate the technical social network, increase the awareness, preparedness, community empowerment, and also the user is this one, international organization, central and local government, private sector, and local community. So if I discuss about early warning system, it's a very complex concept, yeah? Not only the instrumentation, So early warning means, according to the UNISDR in 2010, during the meeting in Bonn, Germany, we have four main component of early warning system. The first one, we need to have the risk knowledge. It has been discussed just now by the two keynotes before me. Risk knowledge, we need to do a lot of investigation, good information, collect all of the data in order to understand what is the danger of this area. And the second one, we need to disseminate and communicate all of what we get to the authority and also the local community. The third one, we need to do this one is the equipment, monitoring and warning devices. This is the equipment. And the last one is response capability. If I hear the siren, what should I do? Should I run to the right direction or left direction? Should I bring my motorcycle with me? Should I bring my refrigerator with me? Or what should I do? So that's why we try to adopt this concept, and we make 7 subsystems of early warning system. So if somebody in all of the world, they are going to compile with ISO, they develop international standard for early warning system, they should do the risk assessment first. No risk assessment means it's not ISO standard. We need to have the disaster preparedness organization. We need to have the evacuation map and route, SOP, equipment, commitment, dissemination, and communication. We have 7 components, and it is published in some of our papers also. You can download. So risk assessment, not only technical, but we need to do also the institutional survey and social survey. And then we ask so in case of, this is in in Banjarnegara and also in Lawu, in Lawu Mountain, we involve the community to develop the hazard map, and this is the result. So they can draw one by one, where is the house, which on this house will go to which direction, they should come here, and this is the landslide. And can you see this one? The north direction is not going to up, because it's going down, because in this way they understand their village better. So we rotate the north direction, and this is what we get from the community. And dissemination, we need to talk, discuss with a good method and material. They should understand even with their local languages, and also to identify the key people there. And we develop also the disaster preparedness and response teams. It is inside the ISO. And we also develop the evacuation map. Okay, can you see this one? The north direction is going down, because when disaster happens, they are not going to go up, they are going to go down. So they don't care about the north direction. They are going to go down. So this is the community hazard map they have. Red colors mean danger area. This is medium. And then they should go to this direction. They should come to the master point in the lower part. And we also plot some of the equipment what we install here. That's for landslide. We also developed the evacuation route for flood. This is in Bojonegoro for the Bengawan Solo flood. So this one, the blue colors mean dangerous area during the flood, and then they should follow the direction and go to the green area. This is the area for evacuation, because landslide maybe not takes a long time, but flood maybe in a week or more than 10 days, when a big floods occur in Bengawan Solo. So we develop also this kind of map. And then SOP, we need to understand, make it very, very simple as we can, that every level. So every level, what is the activities, person in charge, and the notes. For example, in level 2 for landslide, warning, it means we need to evacuate the vulnerable people. We need to evacuate the vulnerable people. This is the main text. But during the 3rd level evacuation, everybody should be evacuated. Okay, then monitoring and warning devices. This is very important. We don't have enough money to put the equipment everywhere, so we need to do the good assessment to select the highest risk and largest number of people affected. So in that location, we put the equipment And then type of equipment also important depending on the geomorphological, geological, geotechnical condition of the area. So how the system works, we by telemetry systems, the longest one was 100 kilometers in Pesisir Selatan that we installed. Let's go to the repeater here, from repeater to the office, and the office can then trick the sirens to warn the people that something is going to happen maybe in half an hour. Okay, that 7 subsystem has been installed in 33 provinces in Indonesia, in 120 municipalities or district. Yeah, this is in cooperation. This is the red colors is flood in 2019, and also we do the landslide in 2019, and then we install also in Myanmar, and also in cooperation with International Consortium on Landslide in Bangladesh and Sri Lanka, and also in New Zealand, in Argentina, so everywhere. So I cannot count it anymore. So this is the standards that we developed and now has been implemented all over the world. One example is how it works. So this is one example. Yeah, early warning system saved 100 households in Aceh Besar in 2015 at the time. So we are going to conduct the evacuation drill at 8 o'clock in the evening. But starting from 2 o'clock in the afternoon, the equipment start to monitor the movement. And then it's going worse in 4 o'clock in the afternoon, and at 6 o'clock in the afternoon, we decide to evacuate the people. So the drill, the exercise become a real evacuation activities, because of the dangers. So we from the academia or research center, we can do the left side. We call it as the flow information. But the local authority, BNPB or the local government, they do the command system. So what we can do is we collect the monitoring data, try to process, and then inform the authority that there is something dangerous is happening now. And then the local authority, they are the ones who decide evacuate or not. So this scheme is very important, because we academia, we cannot ask the people to leave or to evacuate. That's the responsibility of the local authority. Technological innovation, I believe in Indonesia, a lot of innovation we have now. This is ascensometers we developed in Gadjah Mada University. We have 5 patents for this, 5 patents with more than 40 or 50 variants of their equipment. I'm the first inventor, and the second one is Ibu Professor Diko Rita Karnawati. So she leave us with this kind of the big works, to work in BMKG. This is one of the ascensometer, tiltmeters, and then rainfall gauge, inclinometers, many things. So we develop. So this contain of more than 90% of the local materials. So it's made in Indonesia. And then also we install this one in Karanganyar in cooperation with Geomatic department by GPS monitoring systems. And this equipment will send the data to the repeater to the control room. It can trick the alarm on site or store everything in the internet. And this can also, this system will blast the information by SMS, by email, whatever we wish, if the dangerous condition happens. So this is one example of the accessometer graphs, the result of monitoring, tiltmeters, water level, rain graph. We can access everything from the internet now. Okay, that for the landslide. We also develop for lahar or the breeze flow. We install the rain gauge into near Turgo area and several ultrasonic sensor and also camera sensor and also pendulum sensor in order to monitor the movement. So if, for example, the pendulum sensor here move, it means it's very high debris flow will come. In less than half an hour, it will go to downtown of Yogyakarta city. So we have this system also now. And starting from 3 years ago, we changed the ultrasonic sensor, which is not very accurate, with the LiDAR sensor. So we use the LiDAR to monitor the fluctuation of water level in the channel, and also to warn the community if the flood disaster will come. It works well in Kalimantan, one sub-district, Kecamatan, yeah. They conduct the evacuation just a few hours before the flood comes. And then we use also the data from satellite also to, and also we use this method, yeah. We call it as the tank model developed by Japan Meteorological Agency. So if the rainfall come on the ground, it will go to the as the runoff or infiltration or infiltrate inside the lower stratigraphy. So this model, yeah, we can model this one, how much for the runoff and how much for the infiltration, and finally we can model the fluctuation of groundwater level, yeah, by rainfall data by using this tank model. Once we get that one, and then we input into viscoplastic modeling. We have several publications on this, and then we can predict the movement of landslide by using this viscoplastic modeling. So this is one example. The red color, the blue color show the real landslide movement in the field, and the red color is our simulation. So now, once we get the rainfall data, we can predict the fluctuation of groundwater level, and we can predict it move or not. If it moves, how fast it will move. So this kind of model also one of the technological innovation we have. And because I should talk about the disaster mitigation, this is one important slide of what we call as the disaster landslide mitigation strategy. We need to do it in correct way. The first step is we need to do the investigation, good investigation. The second one, we should think what is the causing factors and also the mechanism of this movement. And the third one, we move to calculate the stability analysis of the slope, and then finally we evaluate the best mitigation effort for that. So for mitigation work for landslides only consists of two components. The first one is control works. When we discuss about control work, it means that we change the geometry, make it flattened, and also the water. We control the water with deep drainage system and also the shallow drainage system. And the other one, which is a little bit more expensive, we call it as the restraint works. We use the pile works, like diameter of cast in pile, in place pile works, anchor work, yeah, retaining wall works. So it's quite expensive then. And this is some example. Sorry, because I was graduated from Japan, so I take some example from there. This is the schematic figures of control works. So we have this is what we call as the shallow drainage system, and this one drainage well. This is the deep drainage system, and here we also have the lateral boring to reduce the hydrostatic pressure behind the wall. And also we have the prevention works here. We can see here this is the pile, and this is the anchor work, and we change also the geometry and also the drainage system. So a lot of work we can do for landslide mitigation. And then for there is one example. So if we cannot stop the movement, what will happen? What will happen if landslide move or double flow move? How it move? How far? How fast? How dangerous that movement? So we developed a lot of numerical model. Sorry, I should state it in the beginning because during the conference or other occasion, the audience will ask, yeah, where can we buy that program? No, it's made by ourselves. Yeah. It's mean I'm the main investigator for this program. We developed by our team. We developed the first one, landslide movement numerical model by Navier-Stokes governing equation, and also the recent one is depth integrated model. It has been published, and yeah, you can see I work a lot with Ibu Professor Dikorita Karnawati. So we publish in the journal in US for the numerical model for landslide, rapid movement of landslide and debris flow motion. this is one example. The landslide movement occurred in April 2016 in geothermal area in Bengkulu with more than 4 million cubic meters of the soil mass. It moved and reached more than 2.5 kilometers downstream. It destroyed the geothermal field here. And then we try to conduct the geological mapping there. And then we do the lithological investigation. We need to know each layer by layer of the material. And finally, we implement this our program. So we develop 3 different approach of constitutive model. The first one is hyper concentrated soil liquid mixture flow model. The second one is Fulmi fluid friction and also more column model. This is the best for landslide, yeah. But for debris flow, number 1 is the best. Yeah. And then we try to run step by step the movement. Yeah, it moves going down, and then finally it will stop and close or cover the cluster A of the geothermal field. And then we can install the riverbank protection, sabodam. We install also some sabodams there. And then we run again the simulation in order to understand how the movement will move. Will it go to the same direction or it will change the direction? We can do it by using the simulation. We don't need to construct and then see what is going on. Maybe after 10 years, it will, oh, okay, it still destroy our infrastructure. No, we can do the simulation before that one, and it's available now, the numerical program. And then that for the just now I discussed some equation, governing equation, etc. That for the researchers. This is for the community. When we communicate with the community, we need to use their language. We use some cartoon information. What you can do for if you find the symptom of landslide, the crack, and then what you don't do. Yeah, don't do this one, do this one, and then if we send this poster to the community, they will throw it away. So the method is now we put the calendar down there. Can you see the calendar? Yeah. So in December and then January and February, that's the dangerous time. We need to aware that landslide may happen anytime. But during the May, June up to September, we can do the mitigation effort. Yeah, try to prepare the drainage system, try to do the flattening the slope, yeah, and then also implement the bioengineering on the slope, dangerous slope. So with this calendar, then they take this poster and they put it on the wall, yeah, because there is the calendar there, especially if the calendar have a lot of the red color of holidays. Okay, and also this is for just not for landslide, now for flood. For flood also we develop the poster, what should you do? And then during the flood, number 1, you need to get the good information. Number 2, prepare your house for the flood that will be coming. Number 3, you need to evacuate. You can bring the livestock during the evacuation, and don't forget to bring also some grass, yeah, because you're gonna stay a week maybe. What you can bring, yeah, not more than 20 kilograms. And then the vulnerable groups, yeah, pregnant women, children, toddlers, elderly, and also sick people. And also you need to follow the instruction. Okay, that's all from me. And there's one statement that the hardest challenge is not in the development of the technology, but the involvement of the community living in the vulnerable areas and also effective coordination between the government and other related stakeholders. Thank you very much.
All right. Thank you very much, Prof. Faisal Fathani, for such a great explanations. Yeah. So probably we can summarize that Indonesia is a very prone to the disaster, and we need to shift the paradigm and more concerned to the preparedness, readiness, and resilience. Well, so on behalf of the committee, again, I would like to thank you for your excellent presentations. And let me now give a big applause to Prof. Faisal Fathani. Yeah, thank you very much. Well, ladies and gentlemen, as is followed by the agenda, now we come to the discussion sections. And this is the last sections of the keynote speech. And probably before I present several questions from this chat box, I will give an opportunity to the Zoom audience. Maybe if you have any questions, you can just raise your hand and introduce yourself and also introduce to whom you ask, if any. Is there any question from this audience? Okay, I think we will wait for that. And we have received a lot of questions from the chat box. So I will present the questions in PowerPoint, and we will move to the first presenter for the Prof. Matthieu Kervyn. 1 minute. Yeah, thank you very much for the audience. So, Prof. Matthieu Kervyn, are you still here?
Yes.
Yeah, thank you, Prof. And this is several questions that to you, yeah, Prof. to you. I will read it. Maybe the first one is from Sandy Trigustono. Is there satellite technology to monitor submarine deformations? Remembering the Palu earthquake that caused tsunami because of submarine landslide, it will be very helpful if we can use remote sensing for submarine events. And the second one is what kind of RS, active or passive sensor, that's suitable for flood monitoring, and what parameters would be captured or processed. That is from the question from Ms. Rahma Wardani. And the third one, this is from our students, virtual students, Mr. Akmal Firmansyah. So thank you for the opportunity, Prof. Kervyn. So as Prof. Kervyn has explained before, volcano eruptions can be detected by remote sensing using surface precursor, like thermal, SO2 emissions, surface deformations, and others. But is there any technology that able to detect underground deformations? And if it there, what is the principle? I think this is like similar with the question ones from the Sandy Trigustono. And the last question in this sections for Prof. Matthieu, coming from Ms. Ita Sugiarto, related to the number of events caused geo-hazard in Indonesia. What applications are nearing in the predicting events? Yeah, we have 4 questions, and actually we have another questions, but we will explain for this question first. So please, Prof. Matthieu, if you have any comment or explanation from that. Thank you very much.
Yes, thank you very much for these questions. To tackle the first questions related to submarine events, for so far I know there are no satellites that directly can see under the water. For the Palu events, there has been several applications of remote sensing, including some of them that I've illustrated, to show how the ground has moved within the city of Palu and surrounding area, which already informed about which kind of tectonic event it was. But indeed, it was not directly obvious that the tsunami was triggered by an underwater movement of ground. So I think there are satellites that are capable of seeing the sea surface and look at sea surface elevation. And there are other techniques which are looking at the gravity. So change in gravity related to change of mass at the Earth's surface or within the Earth's surface. I'm not sure such a landslides would generate large enough signals to be detected, but that's the only thing I can think of. Otherwise, you need sensors from boats to look at the bathymetry to look at these deformation. And I think that relates to the question 3. I'm not sure about the underground deformation, if it's meant by that submarine or really below the Earth's crust. Of course, typically when you have a deformation below the Earth's crust, if it's not too deep, it will be translated into some kind of surface deformation. So the general approach is that you detect the surface deformation and then you try to understand or model the origin of the surface deformation, what kind of pressure change or intrusion of material is causing this deformation from the subsurface. But again, another approach is with gravity changes. In the past, we would use gravitometers on the ground, but nowadays I think it is the GRACE systems that enables to detect small change in the gravity fields. But again, this is at rather large scale, so I haven't seen yet applications for things like volcanoes. If I come to the second questions related to the use of remote sensing for flood monitoring, I'm not an expert, but this is definitely being done. Of course, when floods happen, I'm talking about alluvial floods, things that are that raise and recede over several days. Typically, people will use radar amplitude images because they are clouds, so optical images might not be that effective. And on radar amplitude image, the water has a very flat surface and has very limited amplitudes. And so it looks like a very dark surface compared to much more brighter surface when there is no water. So you can really detect where the water is at the moment of the floods. If you are more interested into modeling the floods, then there are other methods to look at soil moisture, for example, to look at rainfall distribution, rainfall intensity, all of these with Earth observations, and these are definitely being used to feed into hydrological models for flood forecasting. The last questions, I'm not so sure to understand what applications are nearing in predicting events. As I mentioned, there are methods that are routinely being used for operational purposes, like thermal imaging, SO2 imaging. So you have websites where you can check any place on Earth for the data of the last day. But this is typically when an event has already started. For INSAR, so ground deformations, there are initiatives, especially in the UK, where they are treating all images coming from any place on Earth. So we are already at the stage where they can detect signals. They use machine learnings to identify abnormal signals. But most of the time it comes as a support when some ground-based monitoring have detected some anomalies, like increase in seismic activity. Then there are specific groups that starts to look at these Earth observation techniques and contribute in monitoring the change of activity. Especially for volcanoes, we have typically several days or weeks to look at precursory signals. For landslides, I'm not aware of things that are done systematically, but when there are either systems that try to forecast landslide periods, like has been shown by other speakers, mostly looking at rainfall and soil moisture, and when you are dealing with slow-moving landslides, then you can put either sensor on the ground and you can complement with Earth observation. So typically, Earth observation is coming as a complement to ground-based systems. They are not replacing it, but they enable us to either reach a more fine scale spatial resolutions, because you have information on an entire area instead of a few stations, or they help to also reach places that are difficult to reach and difficult to install stations for. I hope this is responding to the different questions.
Yeah, that's very great. Thank you very much for the explanation, Prof. Matthieu. Is there any comment from the questioner, from the explanation from the Prof. Matthieu, maybe? I think that's clear. So we have we will continue to move to the second speaker, Prof. Aris Marfai. 1 minute. Yeah, so we will come to the Prof. Aris Marfai as a second keynote speaker. And we have two questions, sir, for you. And the first question is from Matthieu Velasari. Good afternoon, sir. Permissions to ask questions. I am interested in the discussions about the system, about disaster management. And in your opinion, how good is Indonesia capability in the disaster mitigations? Thank you. That is from our students, Matthieu Velasari from STMKG. And another one is actually from me. Thank you very much for very excellent presentations. I just want to ask him, currently, what is the most suitable tool to produce a map of Indonesia in a very quick resolution that used by BIG? Is it from radar, satellite lidar, or from another device? And is there any, advantages from each of these tools? I think that is a question from Prof. For Prof. Aris. If you have any explanation from that, please, time is yours.
Thank you very much, Bapak Moderator. The two questions for me. The first is how good is Indonesian capability in disaster mitigation? Actually, since last 15 years, we learned a lot. We have more knowledge related to the disaster management. We remember that starting from the earthquake and tsunami in Aceh, the Padang, and then Pangandaran, and then earthquake in Yogyakarta, etc., and so on. We learned so much from all those kind of the occasion or these disasters, and therefore, then the mandate from the president to create to have the national agencies of the disaster management following by the regional disaster agencies in the provincial level as well as in the cities level. It reflects that now we are aware of the disaster management. As I mentioned by Professor Fathani, for example, now we are shifting the paradigm from the relief to the preparedness, from the what is mitigation to the preparedness, etc., and so on. I mean, the shifting the paradigm, it's mean that we are more aware about how important that we are dealing with the disaster management. This is the first. The second thing, we can see that the how good is us on the disaster management. We can see from the budgeting politics. I mean, how we allocate the budgets for disaster management. Actually, there is the government. They have the commitments to support always to have to reduce the risk of the disaster by allocating the some budget on that issues. The third thing is actually nowadays, if we have look the people, the society, they have more education, they have more knowledge related to the disaster, not only during the relief, but also during the awareness, increasing the knowledge, the field of disaster, etc., and so on. One of the indication is the school, the university, they are developing the study program on the disaster management, and the school, the university who has the field program related to the disaster, for example, geoscience, geology, geography, and the planology, sociology, etc., and so on. They have always a lot of people willing to enter this study program. It means it indicates that now we are aware, and I'm sure that we are now always increasing the capability on the disaster mitigation. This is in general my answer. The second things, and the second question, how is the suitable tools? According to the PP 45, so we have the new rules on the Peraturan Pemerintah 45 related to the base, how you call it, the development of the base map or pengadaan informasi geospatial dasar, the base information geospatial informations development. So we have three different approaches. The first, especially for 5,000 scale, for the large scale, You can imagine the large of the whole of Indonesia from the Sabang to Morocco is really a huge country. We cannot cover in 1 year. We should have the multi-years project, which is 5 years. And in the scale 5,000 is really big. So therefore, we use the different technology. On the urban area, on the complex area, we use aerial photo plus LiDAR. And the rural area, the forest area, we use remote sensing the images, what we call it citra satelit resolusi tinggi, the high resolution images plus radar. So it's mean we will have the different sources with different techniques in data acquisition, but yeah, for sure different quality. For the urban area, more precision because we use the aerial photo plus LiDARs because we need this one from the complex area, but from the less complex area, for example, rural and forest, we can use the remote sensing satellite. So this is the we combining all those techniques for the next 5 years. Just to give you information, we will do this in cooperation with the BUMN, so the state-owned enterprise. Now we are on the communication with the Kementerian BUMN to have the listing of the BUMN companies who are dealing with the surface and mapping. So this month they do the feasibility study, and hopefully they finish this in April, and then in May we just can have a kick-off for this project, hopefully. Thank you, the moderator.
All right. Thank you very much for Prof. Aris Marfai for such great explanations. Yeah, so I think BIG is very, have a role to the mapping for the Indonesia, and that's also really important to reduce the disaster, at least the natural disaster in Indonesia. Thank you very much. And so we will move to the third speakers. That is from 1 minute, Prof. Fathani. Yeah, we have 3 speakers for Prof. Faisal Fathani. The first one, again, from me. What do you think about the level of awareness from the community in Indonesia now in terms of the natural disaster? Yeah, Mr. Prof. Aris said we have learned about from previous disaster like tsunami, flood, and others, but I think until now, still there are a lot of fatalities when that natural disaster comes. So is it any, maybe the level of awareness of the community is not really good in here in Indonesia? And the second question is from the Johannes Agung. This is our bachelor student from STMKG. Good afternoon. I would like to ask to Prof. Fathani about how is Indonesia disaster risk management, especially on early warning disseminations. Because yeah, PMKG had always give early warning for many disaster opportunities, but why the exposure is narrow? I think there's still have like relationship with the question number 1. And the last one to Mr. Fathani, that is from Mr. Nizar Ahmad. Where are places that underway to gain the ISO standard? How is it going now? So I think this is how to produce the ISO standard, how and why.
Jenengan ngetik boleh telepon itu persis kata-kata kuning nih Pak Danang. Boleh telepon, waduh baru.
Yeah, I think there's 3 questions to Professor Faisal Fathani. Please, should you have any comment or explanation from this? Time is yours.
Thank you, Mr. Chairman. So it's very interesting question about level of awareness. Yeah, I think in Indonesia we have a good level of awareness as long as the community or local authority they understand about the risk. Yeah, so that's why we need to understand. We need to do a good risk assessment, and then we need to communicate disseminate the information to the locals and also to the authority there. So in that way, then we can get a good level of awareness. Different things, because we work also in New Zealand, the developed countries. In developing countries, we have maybe good social engagement, and easy to be motivated to work together to save their nearby area. Because one of the reason, maybe in the developed countries, they pay a lot of tax, so the government should take care of the community at a particular country, I think. So that's why in Indonesia, it's easy, like we have the culture of gotong royong, for example. That's not that easy to do that one in the developed countries, yeah, with that high tax there. So why the fatalities is still a lot. So only related to the awareness, but also we should have only we don't want to put everything, the responsibility, to the awareness of the community, but we need also to do a better governance, a good implementation of the regulation and also policy. And then about the warning, so please distinguish between the warning for the spatial, we call it like spatial disasters like tsunami, volcanic eruption, yeah, and also with local one like landslide and also sometimes flood, yeah. So in case of the like tsunami warning, it can reach so many peoples, yeah, or authority. But for locals, like landslide, it's quite difficult because it's located in a remote area with low educated peoples, and it's a big challenge
Excuse me, Prof. Fathani, I think your connection is not really good, so we cannot hear your voice here.
in the very short time, but the people will then save themselves from the dangers of disaster. And then and of course also the time, yeah, because for flood, we could understand 6 hours before the flood in Bojonegoro if we monitor the water level in Ngawi area, for example. So we can precisely predict that the flood will come. But for landslide, it's quite difficult because it's very local. And in many cases, we could warn the people 4 hours before the disaster, or sometimes 30 minutes before the disaster. Tsunami also, yeah. I know that the MKG Tsunami Center works very hard in order to evaluate if this earthquake potential for tsunami or not, yeah. So that's also the challenge for us. And where we can get the ISO, I suggest you to access first the national standard, nearly similar. National standard, we can, because you know ISO is the organization, and it's a private organization and profit also. So if we are going to buy any kind of ISO standard, we need to pay some amount of money. It's about $100 US, I think, per standard. But for Indonesian standard, we can buy it from BSN, yeah, Indonesian Standardization Agency, or also you can contact Pak Bu Weniza, Pak Rahmat, or Pak Sadli, because BMKG also involved in developing this ISO. they easily will, I think, distribute to all of the students for educational purpose. Thank you.
Okay, nice, very good. There's like, very great presentation and explanation from Professor Faisal Fathani. Thank you very much for that explanation, Prof. So we have like, knowledge how to measure the awareness of the people in Indonesia, and also it can be compared to the developed country. All right, so we still have around 7 minutes. I think we will go back to the first speaker for the Prof. Matthieu. 12 minutes. We still have several questions. Yeah, I think we have 3 questions again for the Professor Dr. Matthieu Kervyn. The first one is coming from the Nizar Ahmad, and he asks, how is it possible to calculate slow movement from just images without online device measurements? And the second one is from Aurora. Excuse me, sir. I would like to ask some questions for Prof. Matthieu. Is the satellite data real time or just taken from some period of time? Then how to access the data? How about the procedure? Is it open for the public or is it only the authority of certain institutions? That's good questions. And the next one, I think this is the last question for Dr. Kervyn, that's coming from Samsul Haryono. What is the proper way to analyze very low quality interferograms, especially close to zero coherence due to dense vegetations? Yeah, we have 3 questions. If you please, if you have any feedback or comment, the time is yours.
Okay, thank you. I'll try to be short because they are very broad questions, so I'll just mention some elements. So for the first question, how is it possible to calculate slow movement for just images without online device? So this refers to the interferometric methods. Actually, I mean, without explaining back the whole methods, it is sensitive to indeed millimeter to centimeter scale movement. Of course, it's always better to have some field information. So, for example, for one of the landslides that I illustrated, we had 15 GPS points that were measured every month. It was not possible to have permanent stations because it's an inhabited area and it's costly. For the other ones, we had the drone images to also provide some higher resolution calibration. But in general, it is possible to have some good information even without field information. But if you want to constrain the errors and check the validity of your measurements, it is better to have some ground measurements. For the second questions, it's related to whether images are available in real time. So satellites are orbiting the Earth every day. More and more we are working with constellation of satellites, so the same sensors on multiple satellites so that you can have more repetitions. So depending on the satellites you're looking at, you have an image every 10 days to every day. This data is becoming available more and more in near real time. So typically after a few hours or a day or two after acquisition, they are becoming available online. It depends also on which satellite you are looking at, but for example, the ESA Sentinel constellation is fully available to the public. So there are, you look at for the ESA platforms, this is available. For NASA, there are also lots of data. For the Planet satellites that I've mentioned, this is not fully freely available, but for academic purposes, it is possible to access quite a large amount of data. And many space agencies are opening their data sets at low cost or at no cost, especially for academic purposes. So I invite you to look into that, or you can contact me if you have a specific request. And then the last questions, what is the proper way to analyze very low quality interferogram? Well, there is no magic. If you have no coherence, well, it's not going to work. So especially in vegetated area, it's pretty complicated. On the other hand, if you are looking at area which are not too heavily vegetated, I do advise that you use time series, so multiple images in which you can filter out some data that are affected by atmospheric disturbance, or maybe some seasons that are less suitable for good coherence. And then by making a lot of pairs, you can actually select those pairs that have the best coherence and evolve towards time series. But if you are in a fully vegetated area, then probably interferograms is not the technique you need for looking at your deformation.
All right, yeah, thank you very much for the explanations that's coming from the Professor Dr. Matthieu. I think that's very clear from the questionnaire. And yeah, because the time is up, so I have to finish these discussion sections. I think there is several questions from the audience, but you know, we need to stick with our time, and the discussion is, I think the time is up. So we, I have to finish these sections. And thank you very much for all of the speakers who give such a great presentations and share their knowledge and experience to us, to audience. And thank you very much for the audience that have like good questions, interactive discussions, and hopefully in this, this seminar will give a lot of advantages for us. Thank you very much, and I will go back to the Master of Ceremony. Please, Miss Janita, the time is yours. Good evening, everyone.
Thank you, Mr. Amir, for guiding this session. And also, we like to thank to all the speakers for sharing with us your knowledge and expertise. Finally, we get to the last session in this event, that is closing ceremony. Ladies and gentlemen, we would like to invite Dr. Munawar S.T.M.Sc as the Head of Academic Administration, General Affairs and Administration of STMKG to deliver his closing speech and symbolically give the certificates to all the speakers. Dr. Munawar, time is yours.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good evening, ladies and gentlemen. We have followed with a series of material exposure from our extraordinary keynote speaker at the 71 World Meteorological Day International Web Seminar. We would like to express our deep gratitude to the speaker who share their knowledge with the webinar participants. We have followed very interesting material presentation and discussion session until the end. Hopefully, the knowledge can be useful for the advancement of science and knowledge in the field of maritime affairs, climate, weather, and disaster. Ladies and gentlemen, this webinar activity is the first international webinar we hold on the annual celebration of World Meteorological Day. This is a very good activity. Hopefully, we can continue to schedule it every year, representing the chairman of STMKG. I would like to thank the committee for the hard work for organizing this webinar event. We don't forget to also convey our apologies for the shortcomings in organizing this event. And ladies and gentlemen, in summary, I would like again to thank all the presenter, audience, and committee for their sharing knowledge and hard work so that this international seminar was run smoothly. We also hope that in the condition of the COVID-19 pandemic, all of us will always be given health and this pandemic can end soon. Finally, I declare the 71 World Meteorological Day International Web Seminar is officially closed. We look to see you again in the next future. Good evening. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you, Dr. Munawar. As the committee, we want to give all of the speakers a certificates which will be symbolically given by Dr. Munawar.
Oh, yeah. Thank you. This is a certificate and key for all presentation for Professor Dr. Matthieu Kervyn. Thank you for being a keynote speaker in an international web seminar. Here for you.
Thank you very much.
Yes. The next for Professor Dr. Renat Muhammad Aris Marfai, Master of Science. Thank you for coming and share much knowledge. We all talk. Thank you for you and this the key for you.
Thank you very much, Pak Munawar.
Yeah. For Professor Faisal Fathani, how are you, Prof? Thank you very much to join in our webinar seminar, and thank you for your presenting and share knowledge for me, for us, for STMKG, more the best. This for you.
Thank you, Pak Munawar. Thank you.
Yes.
Thank you very much for joining the international webinar of School Meteorology, Climatology, and Geophysics 2021. Please accept our deepest apology for any shortcoming happened during the event. Thank you very much for being with us and see you in the next year.
Thank you very much.
Thank you very much.
Thank
Guys,
you, Prof.
see you
Faisal,
later.
Prof. Matthieu,
Prof.
Amir,
Aris, terima
Amir,
kasih.
Pak
Selamat
Munawar,
bertugas ya.
Pak Nyoman, mohon izin live.
Pak Munawar, terima kasih. Pak Nyoman.
Ya, makasih Prof. Aris, selamat bertugas. Sampai
Saya nggak
ketemu
perhatikan
lagi.
ada teman-teman jalan-jalan Pak Munawar ternyata di sini ya.
Terima kasih semuanya, Prof.
Terima kasih Pak
Ya,
Nyoman.
terima kasih.